Thank you. Actually, I'm going to tell you about a bunch of things, but that's one of the things I'm going to talk about. I'm going to be talking about some joint work with Lucas Fidkowski, who's in the audience. This is the archive number. It's a recent paper. And there's some other papers up there that I'm going to talk about, too, by a variety of authors. So one of the main things I'm going to talk about is, and this is going to be, I'm really not going to prove anything. I'm just going to tell a story. So, but draw pictures. All the pictures are correct, unless I make a mistake. But don't expect any proofs. I'm just going to kind of tell a story. So this is one of the main things I'm going to talk about is what's called a QCA, or quantum cellular automaton. And don't read too much into the acronym. It's just called a QCA. I mean, the acronym doesn't really, those words don't really mean anything too useful. So what is a QCA? Well, if you want to, the setting of everything in the talk is going to be lattice systems of qubits. So you can imagine like some square lattice, for example, with 1 qubit per site, or some number of qubits per site, or qubits per site. You can imagine it in 3 dimensions, 4 dimensions, whatever. Just think of some periodic lattice. Could be either an infinite lattice. This is actually a setting which is very easy to talk about, infinite systems. Or you can imagine a sequence of successively larger lattices with some other bounds on how distances go as it goes on. But just imagine some large lattice. And now, given this lattice, you have some operators. So for example, on each side, if there's a qubit, you would have Pauli X, Pauli Y, Pauli Z operators on that qubit. And this allows you to write down some algebra, the algebra of these operators. And the nice thing, for the mathematicians, there's a whole theory of like quasi-local algebra to figure out how to deal with that in the infinite setting. We're not going to need to worry about really any of that stuff. Just you have operators because you have this lattice of qubits. And now, if you want to be fancy, you could say a QCA is a star automorphism of that algebra, of the algebra that preserves locality. But let's put that into much simpler. Let's put that into much simpler terms. So let's say you have some operator O. And I'll use Greek letters like alpha to denote QCA. So you have some operator O, so it might be like a Pauli X on a site. So if you had a unitary transformation on the whole system, some unitary that mapped it, you would imagine some map that U gets conjugated by the unitary, so like U goes to U, U dagger, O, U. Now the nice thing about such a unitary map is that if you have the product of 2 operators, O, O1, O2, it maps to U dagger, O1, O2U, which is the same as U dagger, O1, U, U dagger, O2, U. So this kind of map of this form preserves the rules of the algebra. The product, the map on the product is the same as the product of the map. And similarly, that's the automorphism part. And star automorphism meaning if you stick in a dagger there, it maps to the dagger on the other side. So this is an example of a QCA. So a QCA will in general be some map O going to alpha of O. And I'll use Greek letters alpha to denote QCA. Preserves locality. This is the key requirement. So there's some range R. So if O is supported on some site here, you require that there be some range R so that alpha of O supported within distance R. Support distance R of O. Distance R of O. So a map that preserves locality. So whatever it does, it gets mapped to something nearby. So that's what a QCA is. It's a map of this algebra that preserves locality. You can think about tails. You could say, what if it's mostly supported there, but a little bit, but it can be well approximated, but it has some tail going away. We're not going to talk about that in this talk. It's an interesting question. That's what a QCA is for us. Now, what is an example of a QCA? A simple example of a QCA is a quantum circuit. So a quantum circuit would be a local quantum circuit. So you have some gates. Each gate would be some unitary that acts on a few qubits. And you can say, okay, I have a unitary that acts on these qubits, a unitary that acts on these qubits, a unitary acts on these ones. And you compose them in a small number of rounds. So first a unitary here, 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 and you build it up over a small number of rounds. So each gate, if a gate acts on these qubits, it might take the support of the operator, increase it by a little bit. But if you have a small number of rounds, it gets increased by some small amount. So that is an example of a quantum circuit. So a quantum circuit, or more precisely like conjugation by a quantum circuit, is what we call a trivial QCA. These are the trivial QCA. Trivial QCA. So the interesting thing for us will be which QCA are non-trivial. Are there maps on this algebra that are preserve locality, but are not quantum circuits of any depth, any bounded depth, any O of 1 depth, or any finite depth if you talk about an infinite system, or any bounded depth if you talk about a sequence of systems of increasing size. Are there such non-trivial QCA? So in one dimension, the problem is completely solved. There's a so-called GNVW index. And in 1D, the non-trivial QCA are shifts. Are a shift. So what do I mean by a shift?
I'm sorry, can you
yes.
be precise about what you mean by trivial? Trivial means that it's implemented by unitary.
Which is a quantum circuit. Which is a quantum circuit. There is a quantum.
If I take this, so if I take the same unitary at many, many, many sites, and
okay.
Infinite tensor product of them, which is not in the algebra, that is for you trivial or not?
Yeah, the conjugation by that product of unitaries, that would be trivial. Yeah.
Even though it involves an infinite number of quantum circuits.
Yeah. The quantum circuit is infinitely big, but like everywhere you look locally, it's just a bounded depth. Yeah. So right. I mean, like you'd imagine a picture like this, like in 1D, like, and you know, you can do translationally invariant or non-translationally invariant forms, and actually by a kind of torus trick, there really no difference between translationally invariant and non-translationally invariant. Okay, so the non-trivial QCA in 1D are a shift. So what is an example of a shift? A shift QCA would simply be we have a line, and we, for example, might have a line of qubits, and you could say alpha maps z on qubit I, z sub I means Pauli z on qubit I, is z on I plus 1, and alpha x on I is x on I plus 1. It shifts everything over by 1. Of course, since there's a shift by 2, a shift by 3, a shift by 4. And actually, you can shift qubits, you can shift qtrits, whatever. And so there's actually it gets characterized by a rational number that tells you how much of what dimension gets shifted what way. So you could have a QCA, it's like we shift dimension 5 objects to the right by 1, and dimension 2 objects to the left by 2, and it would be characterized by an index 5/4. 5 for the right by 1, and 4th by 2 to the left by 2. But that's the full characterization in 1D. They're just shifts. In 2D, all QCA are trivial except for like there's a shift. So if you talk about a 2-dimensional system, you can take the 2-dimensional system and just shift the whole thing, but there is nothing else. That's the theorem. At least if the degrees of freedom are spin degrees of freedom rather than fermionic. It's unknown in the fermionic case. So we'll ignore the shift. So we'll just modding out by shift. 2D, all trivial, up to shift. Then in 3D, it turns out that there is a non-trivial QCA. In fact, there's several. And the first one is the first non-trivial QCA, which is not just a shift, is from this paper, 3D non-trivial QCA. And a lot of what I want to talk about is, which is not a shift. It's not just shifting the whole 3D system, is like why these things exist. So I'm going to talk a little bit first about our understanding at that time of why these QCA existed, and then sort of a more recent understanding that Lukáš and I have been in this paper of that I mentioned. So let me first get back to 1D and kind of pose a little bit of a puzzle, which may explain why QCA are interesting. So there's the Kitaev chain in 1D. So what do I mean by Kitaev chain? Here we're talking about a systems of Majorana degrees of freedom instead of, so you can imagine, so 1D, 1 Majorana per site, Majorana per site. And there are 2 phases. One phase is sort of described like this. I don't know if people know what I'm kind of drawing in cartoons. So this would be something like you have, it would be stabilized by like I gamma 2j plus 1. Like every time I draw a little ball around a pair of sites, that means that the product of those 2 Majorana operators has an eigenvalue, a specific eigenvalue. And then there's also this Kitaev phase, which is where you pair them off in the other way. This would be like a non-trivial phase of a superconductor in 1 dimension. Now, is this Kitaev phase, so sometimes people call this like the trivial phase and the Kitaev phase. Is this Kitaev phase topologically ordered or not? Is this a topologically ordered phase? it doesn't really have any interesting excitations. But what it does have is when you terminate it, it has an interesting boundary. At the boundary, it has Majorana zero modes left over. So it has Majorana zero modes left over, but it does not have any anionic excitations to it. Can you disentangle it? Can you take this thing and map it by a quantum circuit back to here? No, you cannot. There is no quantum circuit to map from here to here. However, on an infinite system, if I continued this, if I had an infinite blackboard, a shift by one will simply map this one to this one. So a QCA will disentangle the Kitaev chain, but no circuit will disentangle it. So that was kind of one of our understanding at the time, that a QCA is a way to disentangle these interesting phases that have no anyons, but intrinsically have interesting surfaces. And this is where we came up with this three-dimensional QCA. So there's, yes?
What about the fact that the quantum dimension is square root of 2? Those aren't really qubits.
Yeah. So right. So this is a shift of a Majorana chain. So yeah, and so there is an extension of the GNVW index where you have a square root 2 index of shifting a Majorana. So yeah. So in 3 dimensions, there's a bunch of interesting phases, and in 3 dimensions, there's one phase, the 3 fermion Walker-Wong model. I won't go into much detail about what this model is, but it's another interesting model that has no anionic excitations, but has an interesting surface. And what I mean by has an interesting surface is that when you terminate it on 2-dimensional boundaries, you kind of have to do something interesting. You necessarily have to introduce some chirality at the boundary if you want to gap it out, or some kind of topological order at the boundary if you want to gap it out. You can't just gap it out on a completely trivial commuting projector Hamiltonian at the boundary. There's no way to do that. And this 3 fermion Walker-Wong model is disentangled. It gets just mapped back to the product state by this non-trivial QCA that we found in 3 dimensions. So kind of our understanding at the time is that, oh, this is what, these are why these QCA exist. And actually, the original construction of the QCA was kind of like there was this puzzle, and I think it was Lucas most of it was saying, well, there's this puzzle, is this phase trivial or not? And then Lucas can correct me if I'm sort of mentioning our history wrong, is how we thought about it. And then Jungwon, let me just finish the thought and then I'll get the question there. Jungwon kind of did this enormous computer calculation using his polynomial method, and he constructed this first example of this non-trivial QCA. And when I say non-trivial QCA, since we count the circuits as trivial, a non-trivial one is like a whole equivalence class up to circuits. So there's successively simpler forms of this one. So his first form of it was something like this computer algebra that was like 12 pages written out. Like, yeah, Pauli Z maps 2, and it's just this like enormous thing. And Pauli X maps 2, because it was finite locality, but within some large ball in 3 dimensions. Then later, we got to some understanding as to why it had to exist. And now I'm going to sort of explain even simpler. But let me take the question there.
Yeah, so for those who remember some operator algebra background annoyingly, is there a connection to outer and inner automorphism groups?
You mean like...
On this infinite dimensional system? Because, the one which became implemented by Gates would definitely be inner and somehow...
Yeah. I mean, it's a sort of a similar thought. Instead of answering your question, let me just mention a few properties of these things that and maybe then you can answer your question for me.
That's what I was asking, because if you have if the same unitary is taken everywhere, that's an outer automorphism of the algebra. But you count it as trivial.
Yeah, we count that as trivial. Yeah, we count that as trivial.
Yeah, but the question is whether that's enough, right? You're distinguishing some higher combinatorial properties. Anyway, we will see.
Oh, yeah, okay. So just the thing I was going to mention is an interesting thing is that although these unitaries don't commute, in fact, the QCA themselves, when you like work up to circuits, they form some abelian group. So they commute up to circuits. And actually, the proof of that is kind of like you can follow one QCA by another, and then you realize it's a bit like, maybe Mike can remind me what the name of the argument is when you shift, what's that called?
Swindle?
No, not the swindle. It's the same as this argument that kind of like, well, anyway, okay.
Pi 2 is...
Yeah. So anyway, you kind of follow one QCA by another, and this is time. And then you say, OK, I'm going to imagine a second copy of the system where I do a trivial thing. But then I can take this QCA and precede it and follow it by a swap gate, conjugate the swap gate through the QCA. And because the QCA is local, the swap gate means I've just done some circuit. So actually, it's up to a circuit, it's the same as if I do the 2 copies in parallel. But if I do them in parallel, they of course commute, so I could do this one first, and then I can swap it back. So it forms some abelian group.
Matt, a question here.
Yeah.
So when you say it's non-trivial, it still depends on the fact that 3 fermions not a commuting projectors, right?
OK. Yeah, well, OK, so we don't have a full theorem that this QCA is non-trivial. It's proven that it's non-trivial as a Clifford QCA. There's no way to, the QCA maps Pallies to Pallies. There is no Clifford circuit that realizes that. That's a theorem. It's also a theorem that if it is a trivial QCA, there's a whole bunch of other incredibly bizarre consequences that follow, for one being like that there is a surface that is commuting projectors. So there's, if this is trivial, then there is a non-trivial 2D QCA using fermions, and we know there's no non-trivial QCA that doesn't. And there's a whole. It's not fully a theorem that it's non-trivial, but there's a lot of very bizarre consequences. Okay, so we kind of came up with maybe a slightly simpler way of understanding like why this computer algebra had to find a QCA there, and it relates to this being having no anyons. So if you think about a topological order model, just imagine like the toric code in your head. It's got some terms in the Hamiltonian, like the plaquette terms and the vertex terms. And when you write it down, there's some redundancy in the terms if you do it on a finite system. So like the product of all the vertex terms is the identity, the product of all the plaquette terms is the identity. There's some redundancy between the terms. And this is really associated with that theory being topologically ordered. For this, well, the typical way you write down the Hamiltonian, there is some kind of redundancy between it. But it's possible to rewrite the Hamiltonian so that there's no redundancy between the terms, that there's just a bunch of terms in the Hamiltonian, and the algebra of those terms are completely independent. Any product of them is, look at any product of them, no product of them is the identity. And then you can simply sort of declare, oh, I'm going to declare that the QCA, and each of those terms stays local when you write it that way, maps each Pally Z to some term. Like this term, it maps Pally Z to this term, Pally Z on this qubit to this term, Pally Z on this qubit to this term, and so on. And you just declare that's what the QCA does. There's a little bit of more work to show, oh, and there's also a way to flip these terms. So Pally X will flip a term. And so we call this a locally flippable separator. So it kind of reduces showing that these QCAs exist to taking an interesting Hamiltonian, finding some way of writing as completely non-redundant terms, and then declaring, oh, the QCA maps each of those to some Pally Z. So this was kind of the understanding of where these come from. So now I'm going to start talking a bit about my work with Lukáš, really Lukáš's work in this most recent paper. And I'm going to kind of, well, yeah, just mention one sort of thought here. I'm going to take a little detour before I get back to QCA, but one thought as to why one should be interested in QCA. I think if you're QCA and a lot of things in topology have something in common. You're talking about some object that can't be locally computed, but you can locally compute the change in that object. So what I mean is, imagine you have two like loops in 3 dimension, and you ask, are they linked or not? If you just look near this loop, there's no way to tell whether or not it's linked by this one. But as you move it through, you could say, oh, okay, if I slowly change the loop, oh, the linking changed when one of them passed through the other. And if you look at more complicated things than just whether a loop is linked, you look at some amplitude for some any-on world lines, there may be no way to compute it easily, but there are some rules that tell you, okay, when I change the braiding from this way to this way and overcrossing to an undercrossing, how does the amplitude change? And a QCA is something similar in some kind of moral sense, like, oh, this conjugation is represented by some unitary, but that unitary is not a quantum circuit. It's not some local object. It's not a quantum circuit. The map from an initial state to a final state is not some local thing. But if you start with some initial state and you act on it with an operator, then the operator gets mapped to something nearby. So the way that the state changes is locally computable. So there's some kind of relation between them, and I'm going to come back to that. But now let me talk about something a little bit separate from QCA, but then it's going to get back to it, which is pumps. So this is where this pumping chirality comes from. So one thing we were wondering about is motivated partly by various flow K codes. I guess Dave is going to talk soon about like dynamic automorphism code, but various kinds of quantum codes where things change in time, was what would happen in and some of those pump changes in time can be thought of as pumps, paths of Hamiltonians. And that's starting to get, there's been a bunch of work in 2 dimensions as to what would happen. So Lucas and I were starting to think about what happens in 3 dimensions if you take a 3+1 dimensional system of fermions coupled to a Z2 gauge field. And why would you do that? Well, because fermions coupled to a Z2 gauge field are the same thing as some spin system. And you imagine through this you pump a p+ip superconductor. And I'll tell you what I mean by pump. Why were we interested in this? Well, because there had been some thinking about 2+1 dimensional system of fermions coupled to a Z2 gauge field and pumping a Kitaev chain. So a Kitaev chain is a 1-dimensional object. You kind of pump it through a 2-dimensional system. And this actually is related to some of these interesting quantum codes. So we started thinking about, okay, a p+ip superconductor in 2 dimensions, a 2-dimensional surface supporting a p+ip superconductor, and pumping it through a 3D system. So what do I mean by pump? Well, okay, so first it's easier to draw in 2D. So in 2D, you can imagine some system of fermions all in their trivial state. And you can imagine sort of nucleate a little Kitaev chain, right? And then you can imagine growing the Kitaev chain bigger and bigger and bigger. Eventually, it meets across the boundaries, and then you shrink it here, here, and here. So you can have a sequence where you start with an empty system. But if you want to do it in a way that's sort of more nice looking, you can imagine starting with an empty system. Then you could go nucleate a lot of little bubbles. Then you could go join the bubbles up. Like that. And then finally, you can see, oh, I have bubbles over there, and you could shrink it back to the other system. So you can kind of create the bubbles, join them up, and then shrink it to nothing. So it's really a sequence of Morse moves. Here, make the bubbles, join them along these lines between them to get that, and then shrink the remaining bubbles to nothing. And that would be a pump. In 3 dimensions, there's a similar kind of pump, a little harder to draw. You can imagine creating little balls in 3 dimensions, joining them, joining them, joining them. Now it becomes not 4 steps, but 1 more step to get back to the, well, 3 steps, 4 pictures, but the first and last is the same. So 3 steps now it becomes 4 steps. That you can have a similar picture in 3 dimensions where you're pumping a 2-dimensional surface supporting a p+ip superconductor. Yeah, Mike.
Now, in these pumps, is there a single bulk phase?
Yeah, so the bulk phase is just, say, fermions in their ground state coupled to the Z2 gauge field.
I see, so you're not changing one phase into a different one?
No, yeah, you're just, yeah, it's just a boundary between it and itself. Yeah. Okay, so what does this pump do when you have fermions coupled to a Z2 gauge field? One of the interesting things is that it has some kind of back action on the gauge field. So you could ask, well, what's the state of the gauge field? The first simplest case would be to imagine that not only the fermion's in the ground state, but the gauge field is in its ground state. There are no gauge fluxes anywhere in the system. So if the gauge field is in its ground state, since I've drawn, let's talk for 2 dimensions for a second. Since what I've drawn here is a torus, there's still some topological degree of freedom. Even when the gauge field is in its ground state, there's a topological degeneracy. What is the holonomy going this way or this way around the torus? This is sort of a more local way to think of the sequence of pumps, but it's going to also be convenient a little bit to talk about a slightly less local one, which gives the same answer, which is first you start with here, then you kind of grow it to that, and then you go. So sorry. First you start with nothing, then you make a little ball, then you like extend the ball out in these two directions, then you join, and then you move it up and down and to get back to nothing. This is a little bit of an easier way to think about it. And what you've done here is you've created this little Kitaev ball with a Kitaev chain on the boundary. Now you've created two parallel Kitaev chains, and then you moved one up and one down and annihilated them. And an interesting thing that happens is that depending upon the holonomy of the gauge field in this direction, this Kitaev chain will have either an odd or even fermion parity. And then when you move the Kitaev chain in this direction, you may pick up a minus sign. If the Kitaev chain has an odd fermion parity, you may pick up a minus sign depending upon the gauge field going around in this direction. So you overall pick up a -1 phase if both of the gauge field's holonomies in both directions are -1. So you can describe the gauge field by 1, 1, 1, -1, -1, 1, -1, -1. So these would be like in the two directions of the torus. What is the gauge field? Is it plus the holonomy? 1, 1, 1, -1, -1, and then what is the phase applied? Well, there'll be some non-universal phase, but also there'll be some sort of topological phase, which winds up picking an extra -1 in this case. So what you do is you do some interesting back action. You apply some gate to the encoded qubit. You apply some gate to the encoded qubit. And this gate applied to the encoded qubit, this sort of explains some weird stuff that happens in these two-dimensional codes where electric and magnetic charges can, when you pump them, when you do this, you can change between one and the other. When you go to 3 dimensions, you do the similar pump in 3 dimensions. What you do is you realize a similar gate. I should just extend the table. I have to put in, ones here and then -1s all the way down there. And you only get an interesting phase of -1 when the gauge field is, so I ran out of room, so I'm just going to write some dots. And then if you get -1, -1, -1, then the phase is -1. But otherwise, it's all +1. So what you wind up realizing in 3D, you do a CCZ gate. You do a CCZ gate, in particular non-Clifford gate, on the 3 qubits encoded by the gauge field in these 3 directions of the torus, and you do a particular non-Clifford gate when you do this pump. So that was kind of one of our reasons to be interested in the start for this. But then you start wondering, well, that's the easiest case when the gauge field is in its ground state and the fermions are in their ground state. That's the phase. What happens if the gauge field is not in its ground state? So let's say we have this 3 torus and we have like some flux lines of the gauge field. The gauge field, if it's not in the ground state, there are closed loops, which are flux lines of the gauge field in this 3-dimensional torus. And what happens to those flux lines? Well, a general way to think about it is, a way to think about this CCZ gate that gets realized is to think that this fermionic phase, this p+ip fermionic phase, got pumped through the 3 torus. It got pumped through the 3 torus. It's a 2-dimensional physical system, and it got moved through a 3-dimensional volume. So really the phase you pick up is the action for a 2-dimensional physical system lives in a 2 + 1 dimensional spacetime, and the 2 + 1 dimensional spacetime it lives in happens to just be this like 3 torus you pumped it through with particular boundary conditions. So you have to look at the path integral of this 2 + 1 dimensional p+ip superconductor in the particular 3-dimensional torus you're looking at. So a similar thing happens. You have these flux lines for the gauge field in 3 dimensions. And those flux lines can be thought of as some like world lines of certain defects. You can think of one of the directions of the torus as time. And pumping the p+ip superconductor assigns some action to them. And this action to them, it's basically Kitaev's 16-fold way that depending upon how many copies of p+ip flux you pump through, you assign different statistics to these flux lines. The flux lines are lines, but you can think of them as particles moving in 2 dimensions. If you take one of the directions of the torus and think of it as time. So if you pump a single p+ip, it's rather complicated. 2 p+ips, it's rather complicated what it does. any even number, this topological gate becomes uninteresting. Once you get up to 8 copies of p+ip pumped through, things simplify a lot, and these particles become fermionic, and the back action on those lines becomes -1 to the framing. So you pick up, so these lines have some framing number, and you pick up some back action, which is just -1 to the lines on them. And the interesting fact is that that -1 to the framing is essentially this 3-dimensional non-trivial QCA. So I'll pump 8 copies, induces -1 to the framing, and that is the 3D QCA. Sort of. I'll put "is" in quotes. And it kind of makes sense because pumping these 8 copies, if you had a system with a boundary, pumps some chirality to the boundary, and that's why I talk about pumping chirality in 3 dimensions, and that's sort of this interesting non-trivial boundary phase you necessarily produce. There's a bit of work to show that pumping 8 copies is the 3D QCA, and there's a bit of a paradox. The paradox, I don't know if anyone's going to catch me on this. The QCA is non-trivial, so it's not a quantum circuit. But a pump really is a quantum circuit. If I write a pump like this, it sounds like some very long depth thing. The depth is, first you create it, then you have to move it out to the boundary, then you have to shrink it this way. And this gives a quantum circuit the pump is a quantum circuit, whose depth is proportional to system size, so it's not a bounded depth. But if you do a pump more like this, it's a bounded depth circuit. So you might say, well, is it or isn't it? So that's a paradox, and I'm going to give the resolution of the paradox in a little bit too. That the pump, that the -1 to the framing is the QCA. Well, it relies on, there was this paper here that found some other QCA. Beyond this one, they found some additional non-trivial QCA that not just create like the Walker-Wong one, but also semyon, the 3 fermion Walker-Wong, but also semyon Walker-Wong ones. And they had some simplified form of the QCA too. And the one way to understand this simplified form is going to use an idea of bosonization. We're going to use there's several different bosonization ideas. We're going to use a particular one from this paper. Let me talk a little bit about bosonization and talk about the particular form that you can get, and then relate it to this -1 to the framing. So I mentioned that fermions coupled to a Z2 gauge field are basically the same as a spin system, and this is realized in an idea of bosonization. So maps fermions coupled to Z2 gauge field with Z2 gauge field to spin system. So you have some system of qubits, and it's really an automorphism, not automorphism, it's a map on the algebras. It maps the certain, you have some algebra of fermionic operators and gauge fields. You have fermionic operators, say fermions living on sites and gauge fields on links, and it maps gauge invariant such operators to local spin operators. So it maps only the gauge invariant ones. So you can't say, what is the image of the fermion creation operator on this site? That is not gauge invariant. You cannot say, what is the image of the gauge field operator on this link? That's not invariant. You can ask for the image of the product of gauge fields around the plaquette, or you could ask for the image of something like fermion operator on this site, gauge field on a link to a neighboring site, and then fermion on that site. So you can only ask, so let's say gauge invariant operators. So that's what this bosonization map does. It gives you a dictionary to map one to the other. And a simplified form of this QCA is you have 2. And this bosonization map works in any dimension. And so you have two such lattices. You have 1 One cubic lattice, right? Okay. And then inside it, you have another cubic lattice. Oh, we don't have another color, so you actually have two penetrating cubic. So let's say, so this is lattice 1. And then inside it, which had another color, inside it there's some other, lattice 2. So there's some other lattice 2. And up to a quantum circuit, the simplified form of the QCA from here, is the same as saying, look at the fluxes of the type 1 gauge field. So the fluxes form some closed loops. Look at the fluxes of the type 2 gauge field and compute -1 to the linking number. -1 to the linking of type 1 with type 2 flux. Alpha equals, I'm not sure if I should write equals or I'll write some slightly wavy equals because it's up to a quantum circuit. It's the linking of one flux with the other flux. The interesting thing is this is precisely the kind of thing I was talking about that's locally not computable, but its variation is computable. You can't that is, it's conjugation by this unitary. This is a unitary and alpha is conjugation by this unitary. So is it obvious that conjugation by this unitary gives a QCA, gives some local object? Well, if you take the system, you hit it with some operator, that operator may change the linking of the fluxes with each other. The operator might, for example, be an operator that creates a small loop of flux. But the way in which that changes the phase, if it creates a small loop of type 1 flux, can be computed locally, because you can ask, oh, was that small loop of type 1 flux enclosing the type 2 loop near it? So the phase that an operator that creates a little loop of flux here, it gets mapped to that operator, and then there's some -1 depending upon whether or not there's type 2 flux going through it. So this gives a QCA. It's some object it's local because its change can be computed locally. It's presumably non-trivial. You have to prove it, but it's natural for it to be non-trivial because you can't locally compute what that linking number is. This is not the same as the framing of the flux, but you can turn it into the framing of the flux if you say we're going to take type 1 fermions and run them around type 2 flux loops. Remember, the fermions, the two lattices are dual to each other, but the fermions live on a dual lattice to the flux loop, so the type 1 fermions live on the same lattice as the type 2 flux loops do. And if you run the type 1 fermions around the type 2 flux loops, what that will do is, when you run a type 1 fermion around a loop, it picks up a phase, which is whether or not that loop links with a type 1 flux. And so running a type 1 fermion around a type 2 flux loop will precisely produce the linking of type 1 flux with type 2 flux, because you put a type 1 fermion around these loops, you get a -1 phase if it links with type 1 ones. But there's an additional sign coming in from the framing of where you run the fermion, so that turns it into -1 to the framing of the type 1 fermions. So it's a much simpler form of the QCA. Now, there's this paradox I mentioned. The paradox I mentioned is that it seems like this is it is a quantum circuit. The pump is a quantum circuit. The resolution of the paradox is this all has to do with its action on the fermionic ground state. On the fermionic ground state, it has this back action on the flux lines. It does a certain thing to the flux lines that is -1 to the framing if the fermions are in their ground state. So if the fermions are in the ground state, you can do the action of this non-trivial QCA. However, if the fermions are not in the ground state, the QCA, say the fermions are not in the ground state, but the gauge field is in its ground state, the QCA does nothing, but this pump does something. So this pump does something interesting. So the interesting thing is the product of this pump times this -1 to the framing does nothing to the gauge field, but it does something non-trivial to the fermions. It does some non-trivial action on the fermions, which is interesting thing.
Also possible this is some kind of a doubling. I think it's true that this QCA double to be a quantum circuit, right?
Two copies of this quantum circuit, yeah. The QCA squares the identity, and since it squares the identity by the same argument about moving one copy from one to the other, because it squares the identity, it also means two copies are a quantum circuit. And this also means this QCA trivializes in the presence of fundamental fermions. Here's the really short argument that it trivializes in the presence of fundamental fermions. So if you actually have like fermions there, if you have fundamental fermions, that's the same as saying there's another copy, and that another copy has its gauge field constrained to be in its ground state, because fermions without a Z2 gauge field. And then if you act with the QCA on that other copy, since the fermions are constrained to be in the ground, since the gauge field is constrained to be in its ground state, that QCA doesn't do anything. But so you can say the QCA on this copy times the QCA on that copy is trivial, because two copies is trivial, but the one on this copy does nothing. So in fact, this thing trivializes in the presence of fundamental fermions. Another way to see that it trivializes in the presence of fundamental fermions is, the important thing I mentioned is that you don't have access to the gauge fields. Suppose you had access to the gauge fields. Suppose the gauge field was an operator. Suppose I just had like, not this weird bosonized thing, but I had something where on each link there was a gauge field, which was some, Z2 gauge field that was just Pauli Z on some additional degree of freedom on that link. And I wanted a QCA that was -1 to the linking of, and I had that on both type 1 and type 2 lattices. And I had some QCA that was the -1 to the linking of type 1 with type 2 flux. Well, linking of type 1 with type 2 flux is the same as -1 to the intersection of type 1 flux with type 2 gauge field. That is, if we could put the gauge field on two cells and then its boundary lives on one cell. So if you had access to some local thing whose boundary was the flux, okay, I can to compute this linking is hard, but if I know that this flux is the boundary of some disk, I can just compute the intersection of this flux with this disk. But I don't have access to the gauge fields as local operators. If I had access to them, this QCA would trivialize. And in the presence of fermions, you can then get access to these gauge fields as local operators by some appropriate tricks. Yeah, question in the back.
That's one more question. I'm a little unsecure about how general your gauge field are. Are they given by group actions of automorphisms of the large algebra, or is there even quantum groups, or how general are your gauge fields?
These are just Z2 gauge fields. They're just some Z2 gauge fields. Yeah, very simple Z2 gauge field, yeah. I mean, there's also some more complicated kinds of bosonization, and this may be a recipe to construct more interesting QCA. I mean, I'm glad you asked this question, because I feel that, one aspect of this understanding is like, we're writing down things that involve this gauge field, and they would be trivial if you had access to the gauge field. The gauge field is just for some simple Z2 object. But then you kind of take away your access to it by this bosonization, so you can't see. Yeah, so if there was some more complicated gauge field, but you didn't have an access to that gauge field, maybe you can write down some more interesting QCA and some more interesting maps. But for us, we just understand a Z2 case, yeah. Let me close in like a really kind of speculative way. I've said that, does this actually lead to anything? One thing is kind of, you can start thinking about building up more complicated QCAs with it. One is to build up more interesting 2D QCAs. As I mentioned, these people built up some more interesting 2D QCAs that were really roots of the this 3 fermion one. Really, they built up a 4th root of it. You can use a similar kind of thinking, at least to build up a square root of that QCA in this thing, which is, instead of assigning the gauge fields a phase that's -1 to the framing, you could give the gauge fields semionic statistics. And that gives some, the flux lines, not the gauge fields, the flux lines semionic statistics. You can give them a semionic amplitude. Just say, what the QCA does is it applies an amplitude, which is look at the world lines of the gauge field, compute whatever the braiding amplitude would be if they were semions, and then that's what the phase is. And by a similar kind of argument about the change in it being locally computable, you can build up a QCA. But let me just talk about some conjectural higher dimensional QCA. These is just kind of like, we don't know if these are trivial or not, but I guess, like one of the nice things is sometimes, right, like you do all the work so that then you can just make some speculation, right? So what we have here, so in 3D, what we had is we had 2 gauge fluxes which we talked about linking with each other. Or you could say it was an intersection of a flux with a gauge field. And if you want to count the dimensions, you could say that the gauge field lives on, you could put it on the 1 cells, or dually you could say it lives on the 2 cells, and then the flux is its boundary which lives on the 1 cells. And so now it's an intersection of a 1-dimensional object and a 2-dimensional object. So you could ask about higher dimensional things. Could you start building up some interesting thing in higher dimensions? So a guess, imagine 5 dimensions, 3 bosonized systems, and then you could look at intersection of gauge field of type 1 flux of type 2 flux of type 3. And this is a 4-dimensional, 3-dimensional, and 3-dimensional object. This could be the same as saying it's some linking of the boundary of this with the intersection of the 2 of these. So if you want to say, wait, but you don't have access to the gauge field as a thing, but you can talk about the linking of the boundary of this with these. So the dimensions add up. This would give some local QCA by the same kind of argument that you can locally compute how this intersection changes. Of course, -1 to the intersection number. So it gives some interesting QCA in 5 dimensions, which is a QCA, that it is local. Is it non-trivial? I don't know. Who knows? It's really interesting to me to speculate that this looks like it's a non-Clifford QCA, and Jungwon Ha has some full, there he is. I didn't see it. Full characterization of all Clifford QCAs in all dimensions. And so this is perhaps circuit equivalent to his, but it sort of looks non-Clifford to me. So perhaps it's like a non-Clifford one, and it's a different characterization. So this is a possible 5-dimensional QCA that's outside that characterization. It maybe has some reminiscence to like higher Chern-Simons theory, which maybe makes sense. And you could also conjecture, another interesting one to conjecture is in 4 dimensions. There was some work on, so Jungwon and Lukáš and I did some work on a 4-dimensional theory which was in some beyond cohomology phase. And it was an incredibly complicated construction, but this was some theory with a symmetry-protected theory with a Z2 symmetry, so there were some Ising degrees of freedom and some Z2 symmetry on the Ising degrees of freedom. So you don't require that the thing really be non-trivial, but you're kind of looking at, can we write down a disentangler that's non-trivial if you only allow gates that respect that Ising symmetry? And so then a natural thing to think about is maybe a conjectural, so the beyond cohomology SPT, like maybe this is a much simpler disentangler for the phase we talked about, beyond cohomology Z2 SPT, is that you have Ising degree, Ising type 1 and type 2. You have 2 gauge fields, type 1, type 2, and you have type 2 flux, and which are both 2-dimensional. And then the Ising degree of freedom, which is itself 4-dimensional. And you can look at the intersection of all of them, or you could say look at the linking of the boundary of this with these, or if you want, you could say like, you could look at the type 1 yield and the boundary of the Ising. This might be a nicer way to talk about it. The boundary of the Ising, so this would be 3, 3, and 2, so the dimensions would have. So the Ising domain wall, which is a 3-dimensional object, with the type 1 field, which is a 3-dimensional object, and the type 2 flux, and again, the dimensions all add up. To get an interesting quantity, you can get -1 to this intersection number. It's a possible, much simpler way to disentangle that phase. It is a local disentangler. It is Z2 symmetric. Does it realize the same phase? I don't know, but it's sort of natural to conjecture. So anyway, I think it's an interesting way to talk about these QCA, and I think they're kind of a very interesting object as a kind of slightly different way of realizing a lot of this topological flavor, that, a way of talking about these phases that don't have anyons, but still are non-trivial in some way, like these Walker-Wong phases. So hopefully more work will be done in this area. Thanks for your attention.